Imagine you are holding an empty paper cup in your hand, and someone unexpectedly drops a heavy rock inside it. To catch that sudden weight, your arm has to communicate with your nervous system. A distress signal travels from your hand, up the spinal column, all the way to your conscious brain. But conscious thought takes time. Milliseconds tick by as the brain processes the information, formulates a response, and tries to send a command back down the line. Gravity moves faster than human thought. If you rely entirely on your brain to process sudden physical disruptions, the rock hits the floor. To survive without constantly dropping objects or falling over, human muscles require a localized, ultra-fast autopilot system, a mechanism that bypasses the brain entirely. To find the source of this speed, we have to look microscopically close at the muscle tissue. Most of a muscle is thick extrafusal fibers, the doers generating physical force. Blind to their own stretch, they rely on parallel watchers called muscle spindles. When violently stretched, the spindle gets pulled right along, instantly firing a biological alarm. Bypassing the brain, it hits the spinal cord, firing an immediate command straight back to contract. Simultaneously, the spinal cord sends a second signal to the opposing muscle, like your triceps, commanding it to relax, ensuring it doesn't fight the catching motion. This is called reciprocal inhibition. This self-contained loop happens in a fraction of a second. The muscle catches the cup before your conscious mind even realizes what occurred. But the moment the muscle successfully contracts, it creates a massive mechanical glitch that threatens to break the entire autopilot system. As the large doer fibers shorten and bulge to catch the weight, the parallel watcher trapped inside gets compressed. The spindle bows outward and goes completely slack. A slack sensor is a blind sensor. If another weight drops into the cup while the muscle is already flexed, the loosened spindle won't feel the new stretch, leaving the tissue totally vulnerable to tearing. The nervous system resolves this with alpha-gamma coactivation. While the spinal cord commands the main muscle to fire, it routes a simultaneous secondary signal directly to the tapered ends of the spindle. This pulse forces the spindle's edges to contract alongside the main muscle, keeping its central sensory region pulled perfectly tight. This biological workaround ensures the muscle's safety sensors stay online. Regardless of how wildly the muscle shortens or lengthens, the spindle remains perfectly calibrated to detect the next drop. You have likely tested this microscopic watcher-doer mechanism yourself. It is exactly what a doctor checks when they tap your knee with a reflex hammer. The strike slightly indents your tendon, creating a rapid, artificial stretch in your quadriceps. The muscle spindle is tricked into thinking your leg is collapsing, firing the exact same emergency reflex loop we saw with the paper cup. Beyond the doctor's office, millions of these spindles fire constantly. When you slip on an icy sidewalk, your leg instantly kicks out to catch your center of gravity, often before your face even registers surprise. Your conscious brain acts as the CEO, deciding where you want to walk, but it relies entirely on this hidden, decentralized supercomputer of automated reflexes to actually navigate the physical world.